in this last part of the lecture, we're going to comment on some parameters that define the quality of the communication system, of the wireless communication system we are dealing with. The first one is the signal-to-noise ratio. This is the main parameter we'll have to deal with. And we may call it in two ways, depending on the context, but it's exactly the same. We can either talk about signal-to-noise ratio or carrier-to-noise ratio if there's a modulation involved and a clear carrier is well defined. And the parameter is defined as the ratio of the signal and the noise powers, and those are just the way to represent them. Here we separate, we write explicitly the bandwidth and the noise power spectral density. We have here the definition and the units for those terms. This is nothing more than the power in a bandwidth of 1 Hertz. If your communication system is having a very large bandwidth, you just multiply what happens in 1 Hertz by the total bandwidth. And we use C over N or C over S over N depending on the context. That's for analog systems. For digital systems, things are different. Although the parameters are the same, but you have to introduce other terms. And the terms that you will see associated with the quality of a communication systems in the digital world are either the bit error probability or the bit error rate. And they are represented by BEP or BER, in this case BER. They are the same, basically. In one case, for the probability, that means that you can work some model and establish the probability for density function, and at the end calculate the probability that some bits, certain number of bits will be in error. While the bit error rate is more related to counting errors. For instance, if you toss a coin, you will know that the probability of having heads or tails is 1/2. That's something you know. But I could also begin to throw coins would be the same, but for a coin, I will be just tossing coins, and after maybe tossing 100 times, I will count, and I will have 51 heads, 49 tails, or a different value. At the end, we are talking about the same thing, but probably bit error rate is more associated with measuring the number of errors that occur in a certain number of bits. But those are not the unique terms. Sometimes you will hear about symbol error rate, frame error rate, block error rate, packet message. There are many, many ways, but at the end, you are counting errors. That's the basic tool here. Or you have the probability of a certain number of errors occur during a transmission. And the important parameter here, which is the signal-to-noise ratio 2, but is defined as the energy per bit, EB, to the noise power spectral density ratio. And there's a subtle difference between those two terms. Here we talk about power. This is signal and noise powers. Here we talk about energy. This is the energy in 1 bit, and this is the noise spectral density in 1 Hertz. If you look at the units, noise power spectral density has units of watts per Hertz. Watts are joules per second, and Hertz are cycles per second. So this, although we call it the noise power spectral density in the long way, this is energy. Basically, this is noise energy. And it's equal to K-T systems. This is the temperature, the noise temperature of the system, and Boltzmann constant. Everything else you know, S is the signal power, C is the modulated power in the carrier, B is the bandwidth, N is the noise power. And here you have the equivalent system noise temperature, and now things begin to change, and you are going to see the terms here. First of all is the energy per bit. The energy per bit is just the carrier power times the time duration of 1 bit. and the time duration of 1 bit is dB, and you have it here, and the noise spectral density. But the inverse of the time duration of 1 bit is just the bit rate, the number of bits you send per second. So this is normally represented by bits per second, and you are very familiar with this unit, or sometimes you will be seeing this written as BPS. So look at the expression here. The energy per bit to noise power spectral density ratio is equivalent to the carrier power to noise power spectral density times 1 divided by the bit rate. And here again, you could represent either the energy per bit as the carrier power times the time duration of 1 bit, or you could go the other way and say that the carrier power is equal to the energy per bit times the number of bits per second, which is what you have here. So those are related, but those are the two main expressions for analog and digital systems that will give you the signal to noise ratio. In digital systems, things are complicated. It all depends on the systems you are using. Here you have a simple example where this is a BPS. Okay? This is just the binary phase shift keying. This is just the simple case we saw before. Here you have the bit error rate, 10 to the minus 4, minus 5, minus 6, depending on the system. You could tolerate a number of errors. And here you have the bit energy to the noise power spectral density, if you want the signal to noise ratio for the digital system in dBs. Now, for this typical modulation scheme, when you consider that it only has white Gaussian noise, additive white Gaussian noise, which is just one of the general cases you may consider, then the bit error probability is just a complementary error function, which is defined in this way and is directly proportional to the ratio. So you can plot this figure here, and with this you can find the parameter. And if you want to read this, this is telling you that for this modulation under these conditions, then a signal to noise ratio of 9.6 dBs will be required to have a number of errors that is 10 to the minus 5. That means that you are having 10 errors in every million of bits you are sending. This is basically the parameter that you have to consider. Thus, for this kind of noise, it's a very well behaved and very well known noise, but you could have other different scenarios. You may have, for instance, bursts, or you have some different kind of errors where this modeling is not that straightforward to be used. But this is just the term and the way to proceed. Once you know the modulation, then you could establish the bit error rate that the systems had to work with. And with this, we can summarize this part of the signal to noise ratio in just a simple case, which is the antenna with some kind of losses, if you want, associated with the antenna and noise received by the antenna, and a receiver where we have also the noise factor of the receiver and an equivalent noise temperature of the receiver. Under those conditions, the noise temperature of the system is just the sum of the noise temperature of the antenna and the noise temperature of the receiver. Just add those two. And for an analog link, the signal to noise ratio is the equivalent isotropically radiated power times the gain of the receiver, the free space path loss, all the losses you may also have to consider. This is just the signal part of the expression, and here on the denominator you have the noise, K, the system, the noise temperature of the system, and the bandwidth. And here we are including all the losses. Could be associated with the cables, with the atmosphere, with certain conditions, for instance, if it's raining, or you have snow or ice, whatever you have there. And for the digital system, you write a very similar expression. Up to here is the same. What changes now is that here we have Gateway Systems, which is the same, and now we have the data rate. Instead of the bandwidth, we have the data rate here. And here, instead of having signal-to-noise power, here we have the energy per bit to noise power spectral density. And that's the main thing. You can build on top of this, including other effects, other cables, or other terms you may have there, but this is just the basic tool to study signal-to-noise ratio. In satellite communications, from time to time you may all see another figure of merit, which is the gain to noise temperature of the antenna, is the GOVT of the satellite antenna. And this is just the ratio of the gain of the antenna divided by the system noise temperature referred to the antenna terminals and in dBs. And as an example, you have here one of the typical dishes that we use for receiving at home TV signals from satellite. And this is just the basic parameters for the antenna. This antenna is an offset reflector, is fed here, it has here the low noise converter. Here you have the first stages of the receiver to avoid having cables. And then the signal here will be taken to the home side. Now, with this antenna and this diameter, at the frequency of 11.5 gigahertz, which is in the transmission band of those satellites, the gain is about 5,037 dBs for the antenna. It's a high gain antenna, although it's not very large. Now, let's put some numbers. Assume that the noise temperature is about 100 kelvins. It could be lower than that, but that's a simple number to write, because it will depend on the conditions. If the antenna is pointing near the sun, it will have plenty of noise, or if nearby there are all kinds of appliances or other systems that could be sending interference towards the antenna, could also be high, but under normal conditions, you may have between 50 and 100 kelvins on this antenna as the noise captured by the antenna. And then you have the receiver here. It could be a low noise. The nominal value for this one is typically 0.3, but then if you take into account other elements and what follows afterwards, I'm taking here a 1 dB noise figure for this receiver. That means that the receiver will add 75 kelvins. So the total noise of this antenna plus this receiver is 175 kelvins. If you divide 5,000 by 175, this will give you a GOVT of 14.5 dBs. And this is just the figure of merit, the GOVT of the satellite antenna. And this is an interesting thing because, once again, those ratios tell you that you could trade gain and noise temperature. If you have to improve this figure, you can do it in two ways. You just increase the gain of the antenna for a fixed noise temperature of the system, or you could try to lower the noise temperature of the system as much as you can. And at the end, both have the same impact on the link budget. So those are parameters you can trade and see which one is easier to deal with. Increasing the gain of the antenna means a larger antenna size. Decreasing the noise temperature, in some cases, means using different components, if they are available, just to build the receiver with a lower noise floor. And as a final summary, you have here the signal-to-noise ratio in terms of the GOVT for an analog and a digital link, written both as a linear product of terms or as a decibel expression. And here, the second one. We normally use decibels because by changing one parameter here, you only had to add or subtract. And we can do this mentally in a simple way. While if you use this product form, if you just change one term here, you normally have to go through the whole process or just take some ratios. And this is harder to do. So from an engineering point of view, before the advent of calculators, it was always simpler to deal with this kind of expressions, and they are frequently used today. Because with those expressions, you normally see easily what you can trade and what you can improve, or where you can easily act to change the value and adjust the value to the requirements of the system. We will follow this session with some others on some different cases we're going to study. We'll try to apply those basic wireless concepts to some broadcasting cases, could be from space, from satellite, or from an FM station. We'll also see how spacecraft probes communicate with the Earth, or how a cell phone really links to a base station. We are going to see in detail some of those cases, applying those concepts. And let's just finish this session with acknowledging the authoring and also the recording of this session.